Right. All right. So let's go ahead and get started. My name is Karl Ewald. This is the engineering materials class, and I'm trying an experiment. So I went to a teaching conference this summer, and they set us up with a Surface Pro 3 and CCC Confer. Has anyone used that in another class before, like maybe the computer science classes? And essentially what it does is it's kind of this virtual whiteboard. So I plan to do everything that I would do on a whiteboard just kind of within here, and then record all the lectures so that you can, let's say there's a day you can't be here, you could watch it online. The thing I'm not going to do is try to manage an inside class and an external class. Like I'm not going to, do all the digital raising hand and answer questions online. But if you're just trying to tune in, or you want to go back to something, you can always go back and then kind of revisit the lecture. So, it's an experiment. If you know me, I like to do experiments, but some of them fail. So if this fails, then we're just going to go back and move on and do it another way. But I want to give it a try because I've always felt that one of the challenges, especially with using any sort of like multimedia or nice images or PowerPoints, is how do you guys relive that experience? How do you get to, it's really hard to take your notes fast enough to experience that, but by having these videos, you can always go back and look at things again. And I'll try to make images that are important available on the website. So it does mean we're recorded. I have this little microphone here. I'll try not to say anything inappropriate, but there's no guarantees. You guys are adults. I'm an adult. Just kidding. Okay, so enough about sort of the logistics. Let's talk about me now. Okay, so my name, as I said, is Karl. I go by Karl. I don't need to be called professor or any sort of formal name. Karl's pretty good. I answer to it most of the time. I have a PhD in material science, and I'm going to knock up my water. And I have a master's in material science. So let me just give you a little bit of history. I went to UC Davis in 1986 as an aeronautical engineer. I was pretty fascinated with airplanes at the time, and get a job, work at a pizza restaurant. And life's good, getting free food, but the pizza restaurant closed, and I got this job because I was taking a material science class that my professor was offering to work in this lab, and it was material science. When you compare like building aircraft to material science, it's sort of a different kind of scale, right? If you build an aircraft, you're dealing with big giant teams, and if you're working on material science, it's one guy in one lab with glove boxes and equipment. It's kind of seductive. So I was seduced into the mad lab work, just, mixing powders, burning things, vacuum systems. Has anyone ever had astronaut ice cream? Like that freeze-dried ice cream? Made a full half gallon. You just freeze it in liquid nitrogen, you put it in a vacuum system, it pulls all the water off, and you get like this giant block of ice cream. Anyway, okay, so life in the lab. So then I went ahead and got a double major in mechanical engineering and material science, and then followed up and kept going in the material science domain. And so there's a lot of experimental work, but as anyone who's heard me talk sort of about math and calculus and computation, sort of the revolutions that calculus made for us is that we could predict things and then therefore see patterns in nature, because calculus allowed us to see those sophisticated patterns and see that things really did follow those. what we found is that there's other kinds of behavior that isn't continuous like that. So, for example, has anyone heard of chaos theory? Okay, so a few people have. It's just that there are other domains. Things don't always move smoothly. Turbulence, like complicated flow in a wave, for example, right? That's so complicated. It's not just described by calculus. Sometimes there's other things involved. And so I started looking at them with computational approaches. So I did a lot of programming. And then I worked in the programming field for about 12 years. And then I ended up back here in 2011 teaching again. So the fact that I had worked in industry really changed the way I think about school and what your role is and what my role is. You know, I went through school. I thought it was like this kind of big obstacle course. There's all these challenges, and can I get through the challenges? And what I found after I worked is that working isn't really like that. I mean, it's not about learning something and then being tested on it. It's about taking everything that you know and trying to tackle something that's unknown, to tackle a new problem, make a new thing. Like try to find one little way to trick nature into giving you what you want. And so in my mind, like you guys aren't a bunch of students and I'm not a teacher. I'm like the tech lead and you guys are all my junior engineers. So the way I think about that means that part of my job is to enable you to function well. That's what a team lead does, is whenever you hit roadblocks, I try to help you get past them. So when you reach a topic that seems really difficult to you, I'm the person that's supposed to help you try to get past that. And it changes sort of the importance of the information. So it's not just about recall, but about application. Couple other like kind of philosophy things. You know, everyone heard about the bell curve. Yeah, right. 10% of you are going to get F's, and 10% are going to get A's, and everyone else is in between. That doesn't have to happen on a spelling test, though, right? Why can't everyone learn how to spell the words and, to, which to? I guess that's the complicated part, right? You know, I mean, it's possible for all of you to get A's. You just have to all kind of capture and understand the material well enough so that you can all do it. So in this class, like I don't really grade on a curve, and I make many, many efforts to make sure that you can succeed. If you don't learn it the first time, then how about the second? Maybe the third? We'll just keep going, right? Because this information is valuable to you, and so it's important not just to get the grade, but to actually embody and take in the information. That's philosophy, but that's kind of the way I think about it. So what is material science and engineering? Any thoughts? Properties? Yeah. So properties are a word we're going to introduce and talk about a lot. It's sort of, if you think about the properties of something that's material, what would be a property that you could just think of like in common use? Hardness? Yeah, that one actually has a very specific like material science meaning, but that's true. How hard is it? What are some other ones? Specific heat, yeah, that's a really important one. How much heat can it absorb before, or you know, how much heat does it require to change temperature? Some require a lot, some not so much. Elasticity, that's certainly something we're going to talk a lot about, especially in the first couple of weeks. Does anybody have a good thought of what elasticity is?
Object like the ability to stretch or be and be able to come back and
yeah, it's that come back thing. So if it's elastic, like your socks, you know, you can stretch them out and then you put them on, and or your underwear, you know, they have elastic in them to hold them up and keep them where they are. So it's going back to that original shape. I don't want to go too much into properties right now because we're going to do a lot of that, but I wanted to break it down even to something simpler, like how do you differentiate between science and engineering?
engineering more of application.
Okay, so engineering sort of the application of science or a way of utilizing science? Other thoughts on that? What's science? Research?
Explaining nature.
Explaining nature? Observation, science discovers the knowledge. We have a pretty formal definition of what science is now because we have all this history, but it's, in my mind, if you go back to what, ancient people did, they observed patterns, they recognized those patterns, and they took advantage of them. So recognizing them and knowing what they are, that's sort of what science is to me, and taking advantage of them, kind of what engineering is. It's like trying to find some way of working with it. So one way I think about this is if you've seen this equation. So for engineering, if you've seen PV equals nRT, right, this is a very succinct way of expressing a relationship. But the most important thing is that these variables are all bound together. This one's a constant, or it's constant. It's not a constant, right? It could be a constant. In other words, if I change the amount of material in the system, I can change N. This is a constant. Temperature, volume, and pressure, right? So an engineer or a scientist would just discover this relationship and move on from there. An engineer would look at this and say, it's really hot. How can I make temperature go down? If this is a constant, and this we hold constant by keeping a closed system, how can I change temperature? Right, I can rewrite this equation, so I just have to kind of think of it in terms of T. So I say T is equal to PV over NR. So if I wanted to change temperature, and these two are constant, I can change either one of these, and it's going to effectively change this. So if I hold the volume constant and change the pressure goes down, then the temperature must go down. If I instead hold the pressure constant and change the volume. So essentially what we've seen is the fundamental equation that allows refrigeration to happen. Now refrigeration isn't a natural extension of the ideal gas law. It's someone's ingenuity and saying, how can I take advantage of this kind of relationship to create a system in which there's a hot region and a cool region? And I don't want to go through all of refrigeration, but it's the kind of thing that I'm getting at. So there's the science, which is the descriptions, the relationships, and then there's engineers that are taking advantage of those relationships to try to force the environment into something that they're interested in. Material science as a kind of formal subject matter isn't that old. It's about 100 years old. It really sort of evolved during the Industrial Revolution as a formal topic. But informally, right, it's existed for how long? How long? Yeah, pretty much since humans were around, right? What are the ways we kind of think of the epochs of time and the tools that we made? What are the, how do we talk about that? I don't want to give it away. Yeah, there's the different metals. So we've heard of the Stone Age, right? That was the high-tech material of the day. Why is it, why is that even interesting? Was it really just you could take any rock and turn any rock into a tool? Yeah, so it turns out like, if you're going to make a hammer, pretty much any rock will probably do. But if you're trying to make like arrowheads or knives or axes or other things, then it's really important to find the particular kind of rock that allows you to make those tools. So even then, like, the Stone Age was a very sophisticated time of like searching for the right kinds of rocks, the right kinds of implements, and the way that they were manipulated in order to create these tools. So it was actually kind of a high-tech thing, even though we think of it as just, man. And ooh, yeah, I really wanted to destroy that. Thank you. There goes the surface. Bye, high-tech. Yeah, so there was, there's like already technology associated with the Stone Age. And then what was the next stage? Do you guys remember? the Bronze Age, right? And does anybody remember what bronze is made out of? Copper, tin. Actually, there's a bunch of the kind of metals that come into play there. So essentially, if you could find copper ore and process it to make copper, or if you really just found copper, that's pretty rare, right? One of the reasons that gold and the precious metals were so sought after and so valuable inherently is because if you can imagine, like try to imagine all of the stuff that you know of as high tech, just not around you, you're just walking through the forest and you find a piece of gold. Like it's pretty unique. You can change its shape, it stays shiny, it's not like a rock, it's kind of like a rock. So it was this really incredible material that allowed us to manipulate it. You could change it, you can make it into jewelry, you can make it into all these kinds of items, and it maintained its integrity. There weren't a whole lot of things other than the kind of natural materials like wood that allowed that kind of behavior prior to understanding how to basically process rocks to get metals. And once we learned how to process rocks to get metals, then the Bronze Age started. Copper was abundant, and then the other metals, tin, for example, that got involved, or other ones that were in the rocks, they were mixed and created this new kind of material that you could cast and make other kinds of tools into. What was the next age? Iron Age. And Iron Age is really steel, this incredible material. We'll talk quite a bit about it. Simple idea, and just such a wide variety of options by just manipulating a few external parameters. But we'll talk more about that in a bit. One more thing I want to say, and then I'll take any questions, which is you guys have been kind of like going through this pipeline of mathematics, right? Single problem, single answer, or maybe single problem, multiple answers, two solutions to the quadratic equation or something like that. But it's very concrete, right? There's a right answer and a right answer or a wrong answer. As you went through physics, oftentimes you had right answers and wrong answers, right? There was a mathematical way to describe it. So material science, as it turns out, is not a super mathematically based kind of science. It's mostly observational. It's very visual oriented. So if you're a person that knows you're a visual learner and can function and think really well in 3D, this class is going to be easier for you than it would be for someone that doesn't have those skills of being able to visualize things in 3D. But it's a good place. It's like doing push-ups, When we do crystallography and try to imagine all these atoms sitting out in 3 dimensions, it will really help your visualization skills. I know you guys have good visualization skills because you play video games, right? Has everyone in here played some sort of 3D video game? Yes. So you can translate a 2D image into a 3D idea. You're good at it. The big difference is that like a lot of the boring still pictures that we see, you can't like look around them like this, or at least with the joystick you can turn it and really get a feel for how the thing looks in 3D. At the end of this class, hopefully you can just do that with your mind. How many people can already do that with your mind? You can imagine something like this and just kind of pick it up in your mind and you can see it on all its different surfaces. One of the things, especially for mechanical engineers or engineers that have to visualize things in 3D or design in 3D, it's really important that you start to build that skill. All right. So the importance of this thing not being so mathematical is that you can't just memorize a bunch of equations and then try to decide which equations do I use in this context. You're going to have to memorize a whole bunch of ideas and then organize those ideas together in like paragraphs to explain something like a phenomena. So in that sense, it's almost like an English class or a kind of rhetorical argument kind of class. And it's just your arguments are going to be more convincing and more accurate if they have accurate data that they're using to be based on, right? And that's like all of these concepts that we're talking about are ideas that you then play with to try to describe the world or understand how something's happening. Can you think of other classes where you have to do that? chemistry maybe a little bit, but there's also a lot of math involved. Here we'll have equations, but the equations are more like equations that happen to fit the behavior, but don't have a real physical meaning about like, well, why is it changing? You can't look at the equation and know why it's changing. You can know how it's changing, but not why it's changing. So that's something else that we have to kind of figure out on our own. Any questions at this point? Okay. So I'm going to go ahead and pass out the syllabus. We'll do a little bit of business, and then we'll move on from there. What's that? Yeah, there should be enough for everyone. I just didn't separate the stacks very well. So I think, how many do we have left? One? All right, so that's good. That means all 29 people on the register showed up, and that's fine. You can all join. So if you didn't get an ad code, make sure before you leave today to get an ad code from me. This should be fine. I don't anticipate any issues with it. Okay, so let's take a look at the syllabus. So if you recall, you know, the syllabus is kind of like the contract between the college and you about what you're going to learn in this class, and that's what the student learner outcomes. You're going to learn how to evaluate the properties of metals, polymers, ceramics, composites, semiconductors based on the internal structure of the material. Demonstrate the ability to operate materials testing equipment to generate the necessary data to formulate the properties of materials tested. Definitely will be doing that. And recommend appropriate materials to meet engineering design criteria based on materials properties and performance. And in fact, our first exercise in that will be on Friday in the lab. This is my cell phone number, so if you need to get a hold of me, you can text me at that number. I'm usually paying attention, not always. Sometimes I turn, do not disturb on for a class so I don't get disturbed, and then I kind of forget to turn it back off. I have office hours that are shown here, so Tuesday 1 to 2, and then Tuesday evening for 3 hours, and then Friday morning before the lab. And of course, I'll be around, so if you see me or need me, just make notes. Kyle is going to be our TA, but he's not allowed into the classroom until we have certain paperwork filed, so working on that hopefully soon. Everything here, I think you know, the class is from 9:30 to 10:50. On Friday, we have a lab from 9:30 to about 12:30. It's about a 4-unit course, so in my mind, as you're my employees, I own about 8 to 12 of your hours. So when I think about like asking you to do things like read, I don't just think, oh, wow, you know, they should be able to read 17 chapters in one day. More like, okay, how long does it take me to read the chapter? And I kind of say, does it fit into this kind of timeline? So I'll emphasize many times in this class that pre-reading, reading before we talk about the lectures is going to be really valuable. And on the course website, I'll kind of set out that reading. Even if you just glance through it, just pay attention to the pictures, try to grab the big concepts. Anything you bring to class before it's introduced here will just make it that much more meaningful. And essentially, when I say that, it's going to be cheaper on you in the long run if you're a little bit ahead of me, because then you can fine-tune your ideas using my interpretation rather than listening to me, be confused, then hope the book explains it, and if they don't, then you still remain confused, and then you come back to me, which is fine, but I think it'll be a little bit more efficient for you if you try to stay book. The textbook, I'm using the 9th edition. I know that you can rent it in physical hard copy form from Amazon for about $42, and then you send it back to them. I have, I think, 17 of the 6th edition. Believe it or not, material science isn't a technology or science that reinvents itself every few years, so amazingly, the science in this book is still valid. So, if you'd like to borrow a book at the end of class, you can borrow them. Some of you have already said that I would, so I got to prioritize those people. But otherwise, feel free to borrow a book. The homework problems are coming from the 9th edition, but I've already cut them out of the text and put them together in PDF documents, so you'll have access to them. And then the technical content in there should be fine. How many people have been on the Moodle site, either in a Karen class or an Engineering 5 class? So I'm going to use that as well and kind of aggregate everything there. Depending how the time goes, we'll either try to do that in class or I'll really request that you do it outside of class, especially if you've been through the process. But that's where you'll find the assignments, you'll find links to the videos, these lecture material, everything that you need should be there. You know, you're going to need like paper and stuff for this class. Attendance is mandatory. Homework. So I'm going to use Joanne's system of, it's essentially a 3-point system: check plus, check, check minus, and 0. And if your homework is late, then you just move down 1 rank. So if you're keeping track, right, you could get a possible 3 on the homework. If you're late, then it goes down to a maximum of possible 2. It's already lost 1/3 of the point. The reason I do that is really, there's multiple reasons. One is, I'm not totally naive about like how difficult or hard it is to just go onto the internet and fill out every homework problem and turn in a perfect homework assignment without having done or learned anything whatsoever. It's totally possible. If you feel you need to do that, feel free to do that, but try to learn along the way. I guess I shouldn't say go ahead and do that, because I consider that sort of dishonest, but I wouldn't say that you have to struggle. Like, you should struggle for a little bit, but bang your head on something for 2 hours, you know, go to the walkthrough, find someone else that knows how to solve that problem, look for a solution that will guide you to how to solve that problem, but make sure when you go through it that you now understand it. If you postpone that part, the understanding part, guess what? Yes, that's right. You still won't know it on the test or in another circumstance where you need to know it. I want neat, clean, easy to read homework, but I'm also not going to go through and rigorously correct it. For example, like for the same reasons I told, like you should use the homework as mainly a tool for learning. And if you're a little bit messier than others, but it's clear what your answers are and how you got there, then I'm okay with that. You know, the green engineering paper is nice, but you don't have to. Some people, I don't know, you just like to make it look nice, and that's fine. But if you're not, you just want to kind of get to the learning part, feel free to do that on whatever paper you have available. Lab work. There'll be some like handouts, these workshops. We'll have one I'll give out on Thursday to come back on Friday with. It's just a household items thing. It's not really hard work. There'll be some of those. And then this laboratory work, we're going to write these formal lab reports. And we'll do that as a group, and I'm going to devote a lot of time to talking about that later. There will be quizzes, so whenever there's homework due, there'll be a quiz, short quiz, just to kind of check in with you, let you feel and understand the kind of problems I'll ask, because in a class like this where you have conceptual things, it's really easy to ask conceptual problems, and they may have a kind of yes or no answer. Seems like an easy kind of question, you know, but if you don't know the material, you're never going to be able to choose yes or no because you're not, it's just a random guess at that point, right? So you need to, I'm really going to be trying to give you a feel for the kinds of questions I would ask on an exam. And in order to do that, these quizzes are really just a good way of getting you to understand the kinds of questions we're asking and what they look like. There's 2 exams. You'll have a 8.5 by 11 cheat sheet with your notes on it. There's a final exam, and that is on Thursday, December 17th. Oops. And it's at 7 a.m. in the morning. I usually bring coffee to that, so I'll let you know. And then we're going to have a design project, a group design project. Here's kind of the grade breakdown. You can see there's a lot of different components to your grade here. So your exams will count for about 55%, but all the other stuff does add up. You know, if you miss homeworks, if you don't turn in, if you miss some of the quizzes, 2 quizzes you can throw away, but that's it. The labs are important. This final, I'm sorry, the design project also has a 10% value, so keep track of all that. The withdrawal date, September 12th, to get your money back and not have it on your transcript. To get a W, you need to withdraw by November 21st. If you have a learning disability or have any challenges, let me know. You can be assessed at the Accessibility Support Center and the Learning Skills Program. They can do some assessments, and so if you need any accommodations, please let me know. We'll figure out a way to do that. I'm hoping these videos are a way to help people as well. We're going to try to use as little paper as possible. That's one of the reasons I'm going so digital. And no forms of academic dishonesty are frankly required. If you have a problem, you have a situation, you're challenged, come talk to me. Don't cheat on something. I mean, what's the point? I'm a softie, you know. I'll probably find a way to help you out of your predicament as best I can. I can't do the work for you. I can't learn it for you, but I can find a lot of different ways to accommodate, you know, those challenges that I need to know about them. Don't let it go into the cheating zone. That just will not lead to good things in the long run. Any questions about the syllabus? All right, so I think what we'll do now is I want to get to know everyone in here and take roles. So if you don't mind, what I'll do is sit here and we'll just kind of work around the classroom. Wait, we have one more syllabus left. So I don't know, maybe we'll just move down this row. So what I'm looking for is basically I want to know what's your name, what's your major, and what's some place where materials was important. All right, let's go ahead and get started.
My name is Carl. I'm a mechanical engineering major, and I recently made a skateboard deck. Pretty important material.
Indeed.
I'm Antonio. I'm a mechanical engineering major, and for me, I built a shelf, and I guess what was the important material. My name is Joseph. I usually just go by Joe. I'm also a mechanical engineering major. Let's see, this summer I had an internship where I was working for a mechanical engineering team, but materials involved in designing products.
Mm-hmm.
My name is Marco. I'm also a mechanical engineer. I would say computer chips. So I need to do a lot of things in every day.
Absolutely.
My name is Chelsea. I'm also a mechanical engineer. And then place where materials is important to me would be figure out what was in the material in the kit.
Mm-hmm. Did you figure it out?
No, not really. They don't really tell you.
Yeah.
Like I was Googling through a whole bunch of stuff, and of course,
Yeah.
Honda's not going to tell me in there. Materials are
Could you tell if it was like aluminum versus anything else?
something. It's definitely not aluminum.
Okay, so it's right.
Here,
Yeah.
if it was aluminum, we would just start eating each other.
Yeah.
But it's definitely a hard material. I just don't know what it is. I could bring them in. I have a bunch of them.
Yeah, it'd be fun to see if we could figure it out. But yeah, that's a perfect place where you need a material that can handle the wear and maintain its integrity.
My name's Robert. I'm a chemical engineering major, and I think my Tempur-Pedic mattress pad is very and I really like that material.
Yeah.
My name's Strider. I'm a structural civil engineer, and I used to build custom spear guns. We had to choose materials that could integrate all on it.
Yeah.
There's Ben. I'm also a mechanical engineer. I was looking forward. I think my cell phone has very poor material choice. Sorry, it can fall apart.
Sounds like it.
My name is Jake. I'm a mechanical engineering major. I work for a medium-sized manufacturing company, and I found that it's a lot easier to machine parts on site out of aluminum than trying to do it out of stainless steel. Plastic is also lighter than metal.
Plastic is lighter than metal. Almost always.
My name is Nicole. I'm an engineering major, and I don't know. I didn't really do anything for the summer. I didn't build anything or build anything cool, but last semester, organic chemistry, our project was on converting polyethylene beads back into a fuel that we could possibly reuse in the future. So I guess that's important to me.
Yeah, that's cool.
My name's Cabrillo. I'm a mechanical engineering major, and I would probably say clothes and like shoes is really important because we wear that shit all the time.
I'm Antonio, electrical mechanical engineer. Video is my computer, shares my computer, screen photos. I put on that. Take a look, it's somewhere. Video game. But I ran into a new agency. Getting computers would be pretty common.
What kind of computers? Oh, desktop. Yeah. I just couldn't hear you. It's probably all the rock music.
And I think Ghost is pretty cool. Breaking that is very big. Right? Components of it, and you don't kill someone. Yeah, this is my amendment that I think that if you drug, like, last year, get aspirin.
Wow. Yeah. Mr. Pill.
I'm from Zay. I'm a mechanical engineering major. And I think somewhere with the sales was important to me was in Joanne's last semester for a design project. We had to design exhibit curve and then stand open this fall specifically. And so definitely want to find the right material that can withstand the wear and tear of those little children. I'm Jason. I'm a civil engineering major. And someplace where materials is important to me. I made a model of a flower outward with things I could find dry. Daniel, currently civil, and already finished out the lumber, so, and I work in the hardware department, so
been with a lot of stainless steel, zinc, galvi, and a lot of exterior screw coating. Like there's a ton of them, so I'm trying to get that down and all the wood outside the yard.
Definitely.
Yeah, a lot.
Most people can hear me. I'm thinking there's a corner probably card.
I'm Nick, mechanical engineering, and materials are important to me when I have to do things like my skateboard and my skimboard and all those different resins and fiberglass and what kind of hardener to use and all that. That was a good time.
My name is Janae, and I'm a materials engineer. And I think materials are important every day, every time. There's a really cool book that I read this summer called Stuff Matters, and I considered it again actually because there's so many components to it that I forgot like half the things I read, like what steel is made out of, like kind of. Also, I painted my room the last couple of days, and my room totally doesn't smell like paint. So it's just kind of interesting because I think the materials are changing in them, because I know that like the two that I painted, the whole entire house would smell like paint. So there's some changing in. Interesting. I really looked it up.
Yeah, it's true.
Hello, my name is Ron. I'm a nuclear engineering major. And something that might be kind of overlooked are writing utensils. I take great pride in finding the perfect writing utensil. And the materials, like the polymer blend, like it feels really light. It feels good in my hand. And the steel tip also feels great. Yeah. Don't want it to bend too easily. There you go.
I got pretty nerdy about writing instruments too. It's true. But now I can't hold on to them, so I can't be possessive.
Hello, my name is David. I'm also a mechanical engineer. I think materials is a pretty exciting part of the thing. Bulletproof glass. I think maybe just the thickness of it, just looking at the sensors. Not really sure.
Not just that, but yeah, that's a big part of it. Carolyn.
Right now, I'm actually majoring in materials. We'll see if I'm still doing that at the end of the semester. One of the important things that I'm interested in materials for is my dad is a mechanic, and he tries to only buy crafts and tools because some of the cheaper ones that are made quite with the same material actually had a wrench break that ended off in my hand when I was trying to get it with a hard full box.
You might have superhuman strength.
No,
no, I'm just, yeah. There are bad tools out there, and when they break, it can be really dangerous. Yeah.
I'm Sarah. I'm majoring in ocean science and environmental science. Not sure how possible. Place of material really important to me was when I was drinking water in Latin America, so having a solid filtration. And I'm really majoring in aerospace engineering, and I don't know if it counts, but I like to make cakes and decorate them. Decorate with tile decorating, you need like very thick concoction icing, so they're really soft, moldable like icing, but then hardened, be rigid but not too rigid, for you.
That is absolutely material. Yes, for sure.
My name is Garrett. My major is in mechanical engineering. For me, I was like mechanic, so I mean I'd say 30% on like innovation, that industry is material. That's important.
Thomas, mechanical engineering. I think I mentioned yet, great path. I was in school today. Without those, I would be here. It would wrap around a tree or something. Great path, they have to be just soft enough so it doesn't or little away a little bit, but not too hard that it doesn't damage.
Yeah, absolutely.
I'm Brad. I'll be doing mechanical engineering. I like to do some energizing, and when I started doing that, I had to learn different types of aluminum, and that's all I found out with the trial and error there.
Mm-hmm.
I'm Clay, also a mechanical engineer. I'm putting some materials from Florida. I've got my press line with T. Just the kind of material going there to find the right blend of everything.
Cool.
My name is Jagan. I am the manufacturing engineer / mechanical. And this summer I worked at aluminum as a CNC operator. Machined a bunch of parts for them, so that we use materials. A lot of aluminum, and I've worked with the combination of aluminum and steel powered automotive technician. And also lots of materials. It's always fascinated me. I think that we're a materialistic culture and that we use it all the time and we don't appreciate it. It's really big granted. We just throw stuff away. There's a lot of time that we do. Hello, my name is mechanical engineer, and the answer were important to me. Shoe together, but I can not feel my toes very small right now. So now I'm very shoe.
Shoot.
I'm Charlie. My major is biomechanical engineering, and someplace for materials. I look for lightweight material, put it in a backpack, so it's not so heavy. So that's
All right. Yeah, I mean, materials, like I said, I mean, they're so ubiquitous in our lives, and you know, from innocent things like that we've turned to drinking out of stainless steel, kind of shunning certain kinds of plastics. Now plastics are okay, you know, like they're kind of trendy as well. And a lot of it has to do with costs and manufacturing, recycling, you know, pipeline, like how easy is it to pull materials back out of the waste stream so that we can reuse them. There's so much involved. Okay, so I think what I really want to do is have you guys sign into the course website. So in order to do that, you're going to want to go to onlinecabrillo.org. And if you need to get your password to get on, I think I'll go ahead and pause our recording for a minute. So you'll see the due dates are called out here. This is the mechanical properties workshop. So I have printouts to give to you. I'll give those to you on Thursday. They're just asking you to look at some materials terms and properties and think about physical objects that represent those. So it's not like it's not a lot of work. It's just something I want to give you on Friday so you have one day to turn around to bring them down back to the lab. And then we're going to do the mechanical properties of candy. Some of you may have done that in a different class at some point, but we'll be we'll be exploring that and then trying to make design choices about the best candy to use for various things. I happen to be a big candy fan, as you may know. Okay, so any questions about the website and the kind of information that will be there, what you'll be looking for there? All right, so let's move on. Yep.
So, like I said, today reading chapter 1. So is that what we're going to talk about today and we should read on tonight in the class, or is that what we should already have read?
That's, I wasn't sure how to put that. I had prepped for a while, or like pre-reading. What would be the best way to articulate that? Pre-class reading, pre-lecture reading, just reading? Yeah, but of course we haven't even touched on chapter 1 yet. We have 11 minutes yet. So that wasn't completely surprising. I didn't completely set you guys up for failure yet, but I'm working on it. So yeah. Okay, yeah, so like I said, even if you just glance through it and just kind of look at the topics and try to think how they fit together, what's the point, those are all really good things to do before we hit class. So I'm going to go ahead and start chapter 1 now. So let's see, how do I want to do this? I'm going to go ahead and make a new page. Yep.
So is the homework that you give, any of it going to be coming out of the book or is it going to be coming out from the dashboard?
They will come from the book, but they'll be on that dashboard thing. So I've already cut the problems out, so if you're dealing with a different edition, I mean, there's also, I mean, I gave you guys, I loaned out a bunch of the 6th editions, but there's also 7th editions floating around, 8th editions. I'll see what I can find and try to supply books to the rest of you. But yeah, the homework that you do, you'll have the problem, so you don't have to worry about mismatch of editions or anything like that. Okay, so let's go ahead and look at chapter 1. Whoops. And I'm going to introduce something that I call basically the fundamental theory of material science. And this is really just kind of a chain of thinking. And the way it looks is you have processing, and processing leads to structure, and that structure leads to properties, and then those properties lead to what we call performance. So if you think back, wow, permance. At least I can fix that, maybe. Maybe not. There we go. Performance. I was running out of space, so I just decided to leave out letters. Okay, so the reason that this is so important, or at least so important in my mind, is because it's so indirect. And material science is often this science of indirection. In other words, we take giant vats of metal that we cook rocks, and then we oxidize, right? Usually what happens if you take something like iron oxide, how do you turn that into metal? Any thoughts? Jabin? Yeah, you heat it up, and what happens is usually you provide something like carbon, and the carbon and the oxygen will preferentially bond and create CO2 or carbon monoxide, and then leaves the iron behind. So you end up basically forcing a chemical reaction to get the metal out. And so that's what I mean by processing, and that how you process that, whether you quench it, whether you cool it fast or slow, will lead to different structure, and those different structures will lead to different properties, and different properties will lead to different kinds of performance. So in terms of performance, you know, we already talked about things like the Stone Age, Bronze Age, and Iron Age. So those are really sort of coming from here. Whoops. Go away. Or not. So this would include things like the Stone Age, the Bronze Age. And those made significant, those were significant advancements in human history because of the kinds of tools we could make. We had better weaponry, we had better agriculture. There's a show called Connections. It's this old English guy. They're like made in the 70s and early 80s. Has anyone seen any of those? They're really super cool in a kind of weird way. What he does is he traces back like these core inventions over history and how it leads to something. So you might follow all these inventions, you know, like, believe it or not, someone invented the plow, right? I mean, he probably didn't get credit for it. She didn't get credit for it. But there was someone that actually took and made a revolution in making a metal plow. So the old plows that were just like a stick in the ground and oxen pulling it, when you could have a plow that actually cut into the earth and flipped it over, you made a significant improvement in this one piece of technology, and that allowed you to grow a lot more crops, radically compact the density of human beings into cities that we have now. And so, you know, there's all of these inventions that happen and how they follow through history. So if anyone's ever interested in watching one of those, I have them on DVD. They're really kind of cool because they're just sort of random stops in history, but they show how little design, you know, goes into society. Like, it's mostly about opportunity and luck and chance, and, you know, this guy happened to see this research and then knew that he could do something else. So they're really fun. But essentially, if we look at the Stone Age, the Bronze Age, and the Iron Age, the thing that really changed was the performance, and those things could only come about because until we could process ore and make it into bronze, there was no bronze. It just wasn't something that was around. So this is just sort of an organizing principle that if we go back to this class, or go back to this principle throughout the class, hopefully we'll find some resonance in these ideas as we move through. Properties. We'll talk a lot about properties soon, but I want to talk a little bit about structure. So structure, there's kind of different scales that this happens, so different scales. So we have the nanoscale. And what does nano mean? Yeah, is there a way to be more specific? -9, right? Yeah, it's 10 to the -9 meters. And if you, that's sort of the scale of atoms. So if you imagine, you know, what a meter looks like, and you divided it into 1 billion pieces, that roughly tells you like how big an atom is. They're teeny, right? But we have a lot of stuff that we're going to talk about in this class that sits at that nanoscale. We're imagining these things just, you know, so microscopically small. We're just starting to get microscopes where we can really see atoms, but we are talking about the nanoscale. Then we have the microscale. And micros 10 to the -6 meters. And we find that atoms grow together and build these structures at that scale. So, you know, millions of atoms get together and they create something that exists in almost all metals, all products, which are called grains. And grains are little regions of material that are all organized the same. Have you ever looked when you're crossing a street or near one of those big electrical poles? You can kind of see these geometric patterns. on the metal. And what you're seeing is essentially the structure of the material is large enough, those grains are large enough that you can see them at a macroscopic level. So what we're looking at there is, in this case, not microscopic, but that also exists at the microscopic level. And then we deal with things at the microscopic level. I'm sorry, the macroscopic level. And so in my mind, like macroscopic is starting to get, that's a millimeter. That's something that I can see with my eye. I can really recognize it and see it unaided. So we're going to be talking about structures at all of these different layers and or different scales. And at those different scales, different mechanisms will maybe control how the property behaves or how the material behaves and how its properties manifest. So I'll go ahead and stop there. Any questions, anything I didn't take care of? I think everyone has bag codes. Not everyone has books, but I'll try to round up a couple more. I will see you on Thursday morning. Check the website. I'll try to keep information there for you.